Okay, let's go ahead and get started. So first off, announcements. Don't forget to do chapter 16, the second part of it, tonight. So that's due tonight, 11:55. I know it was originally marked 11:55 a.m. The faster we get started, the faster we can do review, so we may want to get going. Okay, so please make sure you do that. Remember, I lied a little bit last time by accident. It turns out you couldn't quite do all of chapter 17 part 1 yet. By the end of today, you should. So we're going to do a little bit of new things today that will be on the exam, and then we should have plenty of time to do a little bit of review on a couple of the sections that people still seem to be having trouble with. So we're going to hopefully get up to structural or molecular strength of acids today, and then we'll end. Please make sure you bring your ID card and a scientific calculator. Remember, no graphing calculators. Also, your seating chart will be up Monday night. If you have not yet replied to that email that I sent out, please reply to that email. Don't send me a separate one about left-handed seats. Just hit reply, name, ID number. That's all you need. You don't need to say, I want a left-handed seat. If you're replying to that email, I know that that's what you want. Okay, and then last thing real quick, a couple of office hours and review sessions. So tomorrow, I have an extra set of office hours just because my Tuesday ones were really, really busy, and so we really only made it through some of the homework. And so I have another set tomorrow that I set up just this week. It won't really be normal, but for this week. And then there's 2 review sessions. They ended up overlapping a little bit due to room scheduling issues. So the tutors have their review. And they can correct me if I'm wrong here, if you go to theirs, please print off the review packet. It's online on their website, so please print that off and bring it with you so you have all the questions that they're going to go over. Allison, yours is question answer?
Yeah, it'll be question answer unless you come and you don't have any questions, and then I can try to work out some
Okay, so those are kind of your 2 options. So you can go hang out with the tutors for a little while, do some problems that they have set up for you, and then go get all your questions answered with Allison, and you have like 3 hours worth of help there on top of my office hours on Friday. Yeah? It is, so if you click on this, it'll show you, oh wait, sorry. Tutors, it's BS3 1200, so I guess it's here. All right, and then next week, I just kind of shifted my office hours. So I can't have mine after the exam because I have to go grade your exams. Woohoo. But I will have them on Monday instead since that's more useful to you guys. So on Monday I'll have office hours, same place as always, for a couple of hours. I can stick around a little bit later if I have to. I probably won't have my Thursday ones unless people ask. So if people come up to me and say, hey, so I really would like to show up at Thursday 9 o'clock, then I'll have them. But generally morning after exams, no one comes and talks to me. Okay, and of course all your tutors still have theirs. There will not be discussions on Tuesday, okay? So normally you'll have all your normal discussions except for Tuesday afternoon. Any Tuesday afternoon discussions are canceled because I need your TAs to help me grade. So. All right. Okay, let's pick up where we left off. So where we left off was actually starting in on examples on things that we had done and talked about last time. So I'll kind of review a little bit as we go along to refresh your memory. As always, I like doing these on the document camera. So these aren't really any different than what we talked about last time. When you want to find pH and POH, you have to find your concentration of either H plus or OH minus, depending on what we're talking about, and fill into the negative logarithm, right? What we're going to do now is just extend it out a little bit and put some stoichiometry on either side of it, right? So a lot of what makes our problems in this particular class more difficult or more complex maybe is just adding some stoichiometry or some conversion factors to the beginning or end of the problem. And this is what we're going to do here. So now instead of telling you the concentration of H plus or OH minus, we have a solution of HCl made, and I tell you how many grams and how many mils. But we know that. We know that if we put in one HCl molecule, it's going to split up into 1 hydrogen and 1 Cl minus. So if we know how much of this we put in, we know that concentration, then we know this concentration, because all of it gets turned into H+. Okay, we can figure that out. We have grams, we have mils, so we need to convert this into, can we just do grams over mils? No, what do we need to do? Right. So we can take our 18.4 grams, we can use our periodic table, and I'm going to do this all in one step because I think we can handle it. Make sure we convert that into liters. And we get our moles per liter. Ooh, sorry. I wrote down the wrong number. There we go. We get this. Okay. From there, we know, when we originally figured this out, this is actually our concentration of HCl, right? But we know that as soon as we put it into water, it's going to divide up. So it's also our concentration of H+ after it's all had a chance to react. Okay. And I want us to find pH. So what do we have to do with that number? Just take our negative log of it. As we're kind of getting ready for the exam, no on sig figs and negative logarithms and things of that sort. The rules are related to your decimal points and when you take the negative log, how that becomes sig figs. I don't really want us to focus on it. When I used to teach it and grade on it, everyone focused on it so much that they missed some of the bigger picture items. So on the exam, anytime that you have to do sig figs for logarithms or pH, I'm going to tell you how many sig figs. Sound fair? Yeah. If you plan on going into analytical chemistry, come talk to me and I'll show you exactly how to do it. It's not really that big of a deal, but it's not important enough to have you guys stress over it. So I will grade sig figs just like normal and make you guys figure it out for most things, just not when you have to take the negative log or 10 to the power of. I'll just tell you how many sig figs and it'll all be taken care of. Okay. Next one. The next one is pretty much the same idea. It's just with a base. And I ask you to solve for a whole bunch of things. So we have KOH. We have our 5.5 mil. And we have this. How I'm going to do this is not the only right way. There's tons of right ways to do this. Just pick your favorite, but it's how I like going about it. So first off, I ask, what is the concentration of OH minus? That's probably your easiest one to solve for first. What's your concentration of H plus? What's your POH, which is probably what I would actually solve for a second. And what's the pH? Okay. Well, our concentration of OH minus is kind of already taken care of for us. Do we actually have to calculate anything to know that? If our KOH is a certain concentration, once we put that into water, what does that mean about our OH minus concentration? It's the same. Okay, so well, that was nice, right? Done. I would probably do the POH next. If you wanted to do H plus, you could. Then I'm going to do this. Okay, 2 things done. Now, if we want to do H plus, we can do it 2 ways. What do we know about the concentration of H plus times by the concentration of OH minus? What does it have to equal? 1 times 10 to the negative 14th. So we could do that. I like addition and subtraction better. So what I would probably do is say, okay, well, I know that my POH plus my pH is equal to what? Yeah. Which means that if I know this, and I do, then I know that my pH is equal to that. I think that's a little easier, but whatever you want. And then we have to do H+. Now we have two different places that we can work from. Either is okay. There is an argument to be made for doing it off the OH-. Mainly that argument would be that you've had to do less things with that number, so there's less chances for mistakes, and you may want to do that. I'm going to go ahead and still do it off this. So I know that that's my pH, so I can take 10 to the negative pH. And get that. We should check and make sure that everything makes sense. So we added a decent amount of a strong base. What would our pH be? Less than or greater than 7? Greater, and by a little bit or a lot? A lot. A strong base, a good amount of it, and it is. It's really close to 14, right? So that makes sense. We know our POH should then be near 0, right? Because they're going to go opposites. And it is, so that's okay. We know that our H+, because it's a base, should be less than or greater than 10 to the negative 7th. So is a base going to have more or less H+ than water? It's going to have less, right? Acids have more, bases have less, and we're good there. So all of that lines up. There's one more thing we need to do, just pretty much because I asked, and that's calculate the number of moles of KOH. Just some review of stoichiometry and review of what molarity means, basically. So that's not too bad, right? Remember how to do this? We have moles per liter of KOH. And if we want moles, we just multiply by liters to get our answer. So that's a little bit of an aside. You don't really necessarily need that to do anything. It's just a reminder of what molarity is, a reminder that you need to know molarity, and a reminder that once we start getting into reactions happening, that we may need to know that. We might need to actually calculate that on a pretty regular basis. Okay, so quick review of this section. We did this last time, but our main ideas here are our acids and our bases. We have our two types, right? And we talked about the fact that we have weak acids and bases and strong acids and bases. Here, we talked about the strong ones and how to calculate it. And these ones were kind of nice. They weren't too bad, right? It's kind of almost a breath of fresh air after chapter 16. And that's because what we're assuming is that they actually completely break up. And it becomes just stoichiometry, just like what we did back in chapter 5 and 8 and that sort of thing. This becomes a little bit more complex when we do weak acids and bases. Now, I do want you to remember too, it's not written up there, but remember that this is an assumption. We're assuming that it dissociates completely. Under certain conditions, that may not be true. There's actually still a gradient in how much these dissociate, even within the strong ones. So we get to make an assumption, we get to make our calculations really easy by doing this, but it's not actually 100% true, right? There may be a little bit that's still associated together, just not very much. So next what I want to do is talk about mixing these. Taking strong acids and bases and actually reacting them together. This is what we would call neutralization. If they actually reach neutralization. So when you mix a strong acid and a base together, you're adding in a bunch of H+ and a bunch of OH-. And when you add H+ and OH- together, what does that form? water, right? 2 H's and an O, H2O. So we form water that way. And if it's a 1-to-1 ratio, if we add the exact same amount of H plus as we do OH minus, we get a neutral reaction, or we get a neutral solution. Our pH is equal to 7. And that's a lot of the things that we want to do when we're like disposing of waste. We don't want a really strong acid or base. But we want to be able to calculate what happens if maybe they're not 100% neutralized. So if you ever do these calculations and you have exactly the same amount of H plus as you do OH minus, you're neutral and you're done. But what if we don't quite have that? What if we have some leftover H plus or some leftover OH minus? We want to be able to do that. So for all of these that are just strong acids and bases, it's not too bad. There's a few different ways of doing it. I'm going to pick the 2 most common, and we're going to actually do the problem both ways. The way that I tend to like to do it, I like switching everything into moles. And then I like doing a mole-to-mole reaction, because then it's just stoichiometry like we did in chapter 5 and 8. So we can see how many moles of H plus we have, which if it's a strong acid, it's just how many moles of strong acid we have. We can see how many moles of OH minus we have. If it's a strong base, it's just the same as the moles of the base. And we react them on a 1-to-1 ratio, because they react 1-to-1 to form water. Once we do that, we see, okay, is there any leftover? Is there any that we didn't react? That leftover we'll treat exactly like we did the problems in the last section. We'll just take the negative log of the concentration and be done. So that makes a lot more sense when we actually do them, so we'll do that now. And again, I'm going to do it 2 ways. The first time I'm going to do it exactly like I just talked about, so that you can see exactly where everything is going. And then I'm going to show you what is probably a little bit of a shortcut. You just need to make sure you know what's happening when you do the shortcut so you know why it works. Okay, so nothing more new, there's really nothing new here. It's just taking what we did in the last section, applying it with the stoichiometry that we have with chemical reactions. So let's look at it. We have 100 mils of 1 molar HCl and 100 mils of 2 molar NaOH. And we know that these are going to neutralize each other to some extent. What is the pH? Whenever you hear what is the pH, you want to think, okay, I want to get to my concentration of either H plus or OH minus. It doesn't really matter which, you can make it work either way. So we're going to take H plus, we're going to react it with OH minus, and we're going to form water. I really like keeping track of everything in a nice linear down the page fashion next to my equations. So let's go ahead and calculate how many moles of H plus we have. And this is before they get a chance to react. We have 1 molar. We have 0.1 liters. So we get 0.1 moles. Not a step that at this stage in the game that you would have to show me, okay? I'm just showing you so that you know where I got it from, and if you go look at it later on, you know where it came from. We'll fill that into here, just so we know, oh yeah, this is how much H plus we have. This is not really a nice chart. This is me just keeping track of what I know and what I don't know, so that's why I'm not writing ice along the side, because there's no equilibrium here, at least not one that we're worried about. We'll do the same thing for OH. For OH, we have a 2 molar solution, and we still have 0.1 liters. I'm putting moles next to each one. You could also just kind of like write moles along the side if you wanted. Now, these react 1-to-1, right? There's no having to worry about X here. There's no having to worry about whatever. They react 1-to-1 until one of them hits 0. It's a limiting reactant problem. Which one hits 0 first? H plus, right? So how much, all of this goes away. So at the end, how much is going to be left? 0. Since all of it goes away, how much OH minus goes away? Yeah. Okay. Again, not really nice chart. I'm just keeping track of my reaction. Now, I know that I have 0.1 moles of OH minus. So now I have 0.1 moles of OH minus. So what do I do with that if I want to find pH? What should I fill into? We have options, right? I'm probably going to fill into pOH. If I had leftover H+, what do you think I probably would have filled into? pH. Now, can I fill in 0.1? No. Why? It's not a concentration. So, what do I have to fill it in over? Why not 0.1?
Because you mix 100 mils with 100 mils.
And exactly. And this is one of the things you have to be really careful of when you're doing these mixing problems. Your volumes change. You mix 100 mils of one, 100 mils of another, and now they're together. So now you have 200 mils. And we get our pH. I like this way because it traces through exactly what is happening. It says I have this much, they react, I have a limiting reactant problem, I have this much left over, and it's really easy, you could almost think puzzle pieces of putting these together if you had that much time. There is a faster way of doing this, so I'm going to show it to you in case you want to do it that way, because it's fine, it works, but I do kind of like this way the best from a showing people standpoint. So the other way here is to change, oh yeah. Oh yeah, good point. I solved for the pH, or the pOH. What did I actually ask for? pH. So what should I do? Oh, here's actually the problem. I wrote down this. I looked at it, said everything makes sense, we're okay, we're done. So that should be 0.301. And then 14 minus 0.301 is equal to 13.7. And let me move it over and scroll out a little bit. Okay, sorry about that. So that should be 0.301. Double check to make sure it makes sense. The checking to make sure it makes sense here, slightly more complicated, because you need to think about which one you have more of, because you're mixing an acid and a base, right? Which one do you have more of here, the acid or the base? The base. So should it be basic or acidic? Should be basic. Is it? Yeah. So you do have to do a couple extra steps in the checking. Okay. So now the other way to do it. Dilute it first, and then react to the diluted concentrations. Okay? So what we do is we sort of pretend in our head that when we take this 100 mils and we combine it with the other 100 mils, we let it actually dilute itself first. We let the other one dilute itself first, and then we react it as a 1-to-1 ratio. So pick your favorite of these and do that. You don't really need to be able to do both of them. Just pick whichever one you like. So for HCl, when we do dilution calculations, do you guys remember like the little, it's kind of an equation, kind of not, but the little axiom that we use to remember what to do? M1V1 equals M2V2. One of the most handy little things. In a lot of high school textbooks, they use C1V1 equals C2V2. Either way, it means concentration. And here, this is before the dilution. This is after the dilution. We do it for each one. And in each case, we're solving for the final concentration. Okay, so we're solving for final concentration. So I have my initial concentration, I have my initial volume. What's my final volume? Is it okay that I left it in mils? Yeah, it's a ratio, they cancel out, so that's fine. You may have also looked at this. There's an even faster way. You may have looked at that and said, wait, I'm doubling my volume, right? I added the exact same amount in, so my concentration will half. And you could shorten it even more. We can do the same thing for NaOH then. And you can shorten it even more with this one in the same fashion. In this case, we have 2 molar. We still have 100 mils of it to begin with. We mix it, and now we have 200 mils. And same thing there. If you recognize that, hey, we're doubling the volume, so we're halving the concentration, you could save yourself some time there. And now we say, okay, these are in the same reaction flask now. They're in the same volume of water. Now we react it as a 1-to-1 ratio. And we take the big one minus the small one. So in this case, we take NaOH minus HCl. And we say, oh, well, that's our excess NaOH. Or if you want to think about it, our excess OH minus, whichever. And 14 minus the negative log of that. Or of course, doing what we did up here, finding the negative log of it first, then subtracting from 14. The bottom way is a lot faster, especially if you caught this, oh, I'm dividing it by 2. You could do this in the course of about 30 seconds if you know it. That's the big key there. You have to know a lot walking into that one. You have to say, okay, I know what's happening, I know how these are going to react, I'm going to dilute it, I'm going to react it, and I'm done. I think that that's a little bit harder to follow at the beginning than this one, where you're solving for your moles first. But either way that you want to do it is perfectly fine. It's just sort of your learning style is what you like doing. Okay. Yeah?
So unlike most equations where one uses a limiting reactant, we use the excess.
Oh, yeah, so in this case, as far as whether you use a limiting or excess reagent, it just depends on what we're asking for. So this is more in the sense that we want to know what's left over of the OH, because that's what's actually affecting the pH. Where a lot of times before, like let's say I'm not sure why I would ask you this, but for the sake of pointing out something with your question, what if I asked you for the moles of water made? Okay? If I asked you for the moles of water made, which one would you need to use here? You'd use the limiting reactant, you use H+, right? And you'd say, oh, I made 0.1 moles of water. Yeah? And before, that was most of the time what we cared about. Because what we cared about was how much water was actually made. In this case, what we actually care about is whatever species is affecting the pH, which in this case is whichever of these is left over. Okay? Okay, so a real quick review before moving on. Remember when you go to do this, you can find your moles of each one, your moles of H+ or your moles of OH-. There is one thing to be a little careful of. When I did NaOH, how many OHs were there per sodium hydroxide? Just one, right? So one hydroxide per sodium hydroxide. What if we'd used magnesium hydroxide instead? 2, right? MgOH in parentheses 2. So do be a little bit careful of that. Some of your homework problems use those too, and so if you don't notice it, you may be caught off guard. Okay, our last section for midterm 1. Molecular structure and strength of weak acids. I am going kind of out of order in your book for this chapter. I'm staying mostly within the chapter, but I'm moving some things around. So make sure you check out the email on the sections of the book if you're big on using the book. Even more so than moving around, there's actually specific sections of each section. Because I like teaching all the stuff about strong acids first, keeping it kind of together, and then moving on to weak acids. Okay, so with this, these are going to be equilibrium problems when we go to do the calculations. Before we get too involved with all of these calculations and figuring out all of these numbers and all of the pH, I think it's a good thing to be able to just look at them and learn some things about them. Eventually we'll get into Kas and we'll have some numbers and we'll be able to see the strengths of them based on the number. And we'll be able to go back to this and be like, oh yeah, that made sense with what I'm seeing here with the Ka too. But for right now, it's nice to be able to look at them and know something. So we're going to need to review weak acids and bases for just a moment to make sure you remember the difference. And then for each of the 3 main groups, right, so we had our hydrohalic acids, we had our oxoacids, and we had our carboxylic acids. For each of those groups, we want to talk about why some of them are stronger than others. This will also be nice because if you have your strong acids and bases memorized, it'll help you see some of these too, or vice versa. Once you learn this, it'll help you memorize some of your strong acids, whichever way you like learning the best. Okay, first off, remember what a weak acid or base actually is. It means that it doesn't ionize completely. Technically, none of them ionize 100%, but in some cases, we can assume it. And those are the strong acids and bases, and we'll actually talk about some of them in here too. But then within the weak ones, there's also a gradient. Some weak acids are stronger than others. Some weak bases are stronger than others. And we want to know why this is. For all of these, it's going to be about stability. When we take and we ionize these, this NO2 minus here wants to pick a hydrogen back up. That's why we say the equilibrium lies really far to the left. Because every time that breaks apart, the reverse reaction happens in a hurry. So it breaks apart, hurries up and picks it back up and goes backwards. Okay. So all of this whole section, is going to be about making this anion, whichever anion it happens to be, stable. Where it doesn't necessarily need to pick that hydrogen back up as much. And that's what we're comparing, okay? In each case, I'll give you kind of a short answer and a long answer. The short answer being, hey, this is how you identify it really quickly, 3-4 words on how to get the right answer if I say compare these two. And then for each one, we're going to talk about why too. I definitely tend to ask why questions on exams, so make sure you do pay attention to both. Okay, so first off, let's look at our hydrohalic acids. Again, most of these we actually know as what kind of acids? There's like 4 of them, and 3 of them we call what? 3 of them we call strong, and there was one missing one that wasn't in the strong acids or bases, or excuse me, strong acids. When we go to look at these, we want to explain why that is. Why is HI a strong acid and HF isn't? And for that matter, I said even within strong acids, there's a little bit of an assumption there that they all ionize. They really don't. So within those 3 strong acids, which one's the strongest of the strong acid, right? Walking into like a strongman competition and being like, okay, everyone here is really strong. Who is the strongest? We can do the same thing here. So we have 2 competing forces. If we were to look at this as chemists, not as Gen Chem students being told something, but saying what happens here, we'd come to up to 2 different things. And we might have 2 different people arguing 2 different sides. Might have one person saying, okay, I know how polarity works, and I know how electronegativity works. Which one's more electronegative, F or I? So our electronegativity goes up as you go that way, right? So which one's more electronegative? F. So which one, if someone is arguing this side of the thing, what one would want to keep a negative charge the most, F or I? HF, it's most electronegative, it wants that negative charge more. So it's happiest as a negative charge as compared to iodine, which means it spends a lot of its time dissociated. That would mean that it's strong, because it spends a lot of its time apart. A lot of its time as H+ and F-. And that would be a pretty valid argument. That makes sense. But there's something else that's happening too. The other thing that is happening is your enthalpy. And so we need to look at both of those when we go to do this. So according to enthalpy, we have this big, long bond when we have HI, right? So let's think about our radii. As you go down the periodic table, what happens to your radii? Your radii increases. So you have HI, which is this giant bond length, and you have HF, which has this little tiny bond length. The HI is going to split up easier because it has that long bond length, and according to enthalpic reasons, it stays dissociated. So two sides of this argument, both are really valid. You could see having, two people having this argument and saying, well, F- likes to have a negative charge. It wants to be the ion more. And you have somebody else saying, yeah, well, HI is a longer bond length, and so I wants to be the minus charge more. Both are really good reasons. So you actually either have to do the calculations out or run the experiment. And we kind of already know the result. There's a little bit of a spoiler because I already talked about which ones are strong and which ones are weak. So which one wins? Well, which one do we know is the strong acid, HI or HF? HI. So the bond enthalpy ends up being the winning force here. Okay? Both are really good reasons. Both really make a lot of sense. And if we were arguing this without any other knowledge other than which one is more electronegative and which one has the longer bond, we wouldn't necessarily know. Turns out that the bond enthalpy is the main factor here. And this sort of discussion of, wait, the world doesn't just make everything nice and easy for us is pretty common in chemistry, right? There's lots of arguments between people, especially in the theoretical side of chemistry, where you can't just run an experiment. You give this sort of issue to an experimentalist and they're going to be like, who cares, let's just run the experiment and see what happens. You give it to a theoretician group and they're probably going to sit and argue about it for longer than it would take to run the reaction. But you can see with ones where maybe we can't. For whatever reason, with different problems in life and chemistry, we can't just test it. This sort of issue comes up. Here, though, we get to test it, which is nice. So we can see that I- is going to be our stronger one. And therefore, that bond enthalpy is the stronger force. So we declare all of these strong, right? All of these I told you to memorize as strong acids. In all cases, we can treat them like the equation or like the problems we've been doing. But there is still a gradient in there. HI is going to be your strongest of those three strong ones, which, depending on how you like learning, makes some of your either learning or memorization easier. You either get to remember this reasoning based on the fact that you know these are strong and this is weak, or knowing these reasonings, you can remember that this is your weak one. Okay. This one goes for the last one too. It's a little more straightforward in the next two groups. The more you stabilize the anion, the less likely it is to go pick that hydrogen back up, and the stronger the acid. Okay? This is the theme for the next few slides. Stabilize the anion, make it want to stay as an anion more, and you'll have a stronger acid because they're going to dissociate more. Remember, we'll go back. Remember, we have our oxoacids. They don't have all of them here. We're recognizing them as these central elements with a bunch of oxygens around them, some more than others, and hydrogens attached to the oxygens. Yeah? All right. So when these dissociate, hydrogens come off, leaving negative charges, leaving those as anions. They come off at different times. So one hydrogen will come off, then another hydrogen will come off. But we want to compare the first one, the first hydrogen to leave. So we have two different things we can change here. We can change the central element, So something like if we look at phosphoric and sulfuric, actually, let's do this, sulfuric and phosphoric. They both have 4 oxygens around them, but the central element is different. In one case, we have a P, in one case, we have an S. The other thing that we can do is change how many oxygens are around it, okay? Keep the same central element and change how many oxygens. So first, let's look at this one. Let's look at a case where we have different central atoms, but same oxidation number. We don't really know about oxidation numbers yet. And thankfully, we don't really have to for this section, because we can kind of do a little bit of a simplification cheat sheet around it, which we'll use until we actually learn about oxidation numbers later on. So here, your strength increases with the increasing amount of your electronegative central element. Let me rephrase that a few different ways. What that means is that whichever acid, if you have the same number of attached groups, whichever acid has the more electronegative element in the middle is your stronger acid. Okay? Now, let's think about the reasoning for this. Reasons are important. You have, if you remove a hydrogen here, you have a negative charge there, right? You have more electrons there than you do protons. That's what a negative charge means, more electrons than protons. Because of that, you need to distribute that negative charge. It's already done for the atom, regardless of what the central element is, in some ways, because you have resonance, right? You have all these resonance structures that you can make, so that helps out. But also, if this is an electronegative element, it will keep some of the electron density for itself, because it's holding more of that electron density. That's what electronegativity means. So reminder, we mentioned it already, which direction as you go up the periodic table, what happens to your electronegativity? And as you go to the right, what happens? So which is your most electronegative element? Sorry, good. So don't forget those trends, it comes in again here. So let's look at an example. Oh, the other thing then that happens, let's talk about here, is if we have different numbers of attached groups. So comparing a sulfate to a sulfite, or comparing a phosphate to a phosphite. What happens there is, let's look at, well, we'll look at examples in the next slide. But what happens there is that we increase the number of places that the negative charge is distributed to because of resonance. So if we take off this hydrogen, we put a negative charge there. That negative charge has options on where it can go, and that helps out. We have more resonance structures. That helps out. And we have a higher oxidation number, which we'll talk about when we get to electrochemistry, which helps out as well. Because the way that the electrons are distributed makes it so that the central element doesn't have as much electron density on it. Okay, so 2 examples, one for each. First one, let's look at these 2. Everything about them is pretty close to identical, right? The only difference here is your central one. One has a chlorine, one has a bromine. Which is more electronegative, the bromine or the chlorine? So come over to our periodic table, we say which one is further up and to the right, and we start with fluorine, and then what's our next one? Chlorine. So chlorine is our more electronegative one, all right? Now, it's more electronegative, so it's going to take more of the electron density toward itself than what bromine would, meaning that overall, that's going to be your stronger acid, because it's willing to spend more time dissociated, more time as a negative ion than the other one. So your short answer is, well, whichever one has the most electronegative central element, that's your strongest acid. All right? Most electronegative, strongest acid. The longer answer is, that's because that electronegativity of that central atom helps to stabilize the negative charge that happens because of that dissociation. Our next one, we kind of have to do a little bit of a cheat around. Actually, quick show of hands. Who knows how to figure out oxidation numbers? Okay, yeah, that's fine. Not a big deal. We'll go over it in detail when we do the chapter that really matters for that. So as you increase your oxidation number along your central atom, the strength increases. Now, the simple way around that is the more, and it works for all the oxoacids anyways. It's not universal because it's a little bit of a cheat. The more attached oxygens you have, the stronger the acid. So that makes a nice little workaround until we can talk about oxidation numbers. So for right now, I'm just going to show you the oxidation numbers, and we'll talk about how to do that later on in electrochemistry. But for right now, I'll just show it to you. Now, using the rule that more attached oxygens equals stronger, which one's your strongest? Do you remember the name of this one? That formula, yeah. You guys remember the name? Yeah, perchloric acid. Don't forget your nomenclature. So this one's perchloric acid. What's this one? It's not perchloric because it has one less oxygen, so it doesn't have the per anymore. It's just chloric. Chloric, right? So what's this one? Chlorus. And what's this one? Hypochlorous, right? So that's the one with all four of them. It's a good place to review nomenclature. The more general version, because most of them don't actually have four like this, whenever you have an ion with an ATE ending, what's your ending for your acid? IC, IC. And what happens if you have an ITE ending for your ion? It's an OUS ending. So don't forget all that. If you're having trouble with it, just come talk to me in office hours and we can go through it in detail again. Okay, so those are your two ways of doing that. Central atom, if your central atom is different, the more electronegative one is stronger. If you have different numbers of attached groups, the one with the most attached group is your strongest. Okay. Next one, or last one, I guess, carboxylic acids. For your carboxylic acids, same rule applies. It's stabilizing the negative ion. You always want to stabilize the negative ion. So this is the group that kind of looks like this. And R is just some sort of hydrocarbon or something else attached. And when that H dissociates, you get this. Right? Now there's one thing that already helps this, that already makes it stable. And what is that? What do we is this the one and only true correct Lewis structure for this? Or condensed structure for this? No, because what else is there? Starts with an R. Resonance. So it goes back and forth like that, right? And all of the carboxylic acids have that. And that's why that hydrogen comes off. We're going to talk in a minute, just for comparison's sake, something that isn't an acid. And the reason why it doesn't generally make acidic compounds is because it can't do this. But carboxylic acids can. So that's why it's able to do it, because it's already partly stabilized. Okay. So now are things that make it more stable, are things that make it stronger. Because within the carboxylic acids, there's different ways to make it stronger. It's whatever is going on with the R group, right? Because that's the only other thing we have here. We can't change the COO structure. That's set, that's our carboxylic acid. What happens is what happens to the R group? Are we changing anything on the R group? Now, before we talked about with the oxoacids that if we had a really electronegative central element, that helped out. It pulled some of the electron density toward it. The same thing is going to happen here. If you have a bunch of electronegative things on your R group, it helps pull some of that electron density and it helps stabilize it a little bit. And that stabilization makes it less likely to run out and pick up another hydrogen, more likely to stay apart. And the more it's stabilized, the stronger the acid. Okay, so 3 examples. This one, we just have a CH3 group. Nothing really electronegative about that. It's just a CH3 group. Okay, that we can make a stronger acid by adding electronegative groups. So instead of a hydrogen, what if we put a bromine here? Well, once we put that bromine there, Now that bromine helps pull a little bit of the electron density toward it, helps ease that negative charge a little bit, makes it a stronger acid. It's bromine. If we put a chlorine there, something that's even more electron dense, or more electronegativity, pulls even more of the electron density toward it, which makes it even stronger. I don't have it up here, but what if instead of this, I put a chlorine here like it is, and then I added another chlorine here? What do we think that would do? Even stronger. Now, this, we're not going to go any more in detail than this particular slide and the next one. But when you start getting into organic chemistry, there's a lot more to do here, okay? So this is sort of a tip of the iceberg of organic chemistry. The only other thing that I want to talk about, and we're not going to talk about why for this. The going into the whys here isn't super helpful, is aromaticity. Think back to 1A probably, and we talked about these things called aromatic groups. And the main one that we had was called benzene, right? You recognize it by this double bond, single bond, double bond, single bond. It's a little more complicated than that, but that's pretty much where we stick with for Gen Chem. Having that also helps, okay? So this is kind of a slide of giant oversimplification, but that it's okay. So if you think of aromaticity as this alternating double bond, single bond pattern, when you have this in your R group, that also helps stabilize it. And you'll learn why next year. Okay. I do want to talk about something that isn't actually an acid, but sometimes people get confused about whether it's an acid or not, and so I want to clarify it here. The difference between what we call carboxylic acids, which we've been talking about in alcohols, okay? This is a carboxylic acid. That is acidic. See the difference here? There's no OO, it's just an OH group. This is what we call an alcohol. That is generally not acidic. We say effectively neutral. We're just going to call it neutral here. This is acidic because of what I showed you a couple slides ago, that resonance structure. And as that resonance is happening, it makes this ion, if you take this off, so you're imagining that goes away and you put a negative charge there, it makes that ion more stable because of that resonance. This, if you take away that hydrogen, is there anything to help out that negative on that oxygen? Nope. And so this is not an acid. Big red letters, red pen if you had it, not an acid. Yet your carboxylic acids are. So make sure you recognize the difference. I throw up these just so that you know it. Alcohols generally have an OL ending. You'll learn about that later. We're not going to test you on it. It's organic nomenclature. None of that's going to be tested for naming. Just know, not acidic, right? Okay. Oh, this is one of my favorite deep thoughts for the week. Let's hope this one doesn't get me in trouble, but you know, whatever. Deep thought for the week. Technically, according to chemistry, whiskey is in fact a solution. But not for you guys because you're too young. Sorry. You probably don't even know what whiskey is, but that's okay. Okay. Let's do some examples. I have three things. Three things that I tried to pick that don't really look much like acids to you on purpose. And I say, rank them. So in each case, we have two hydrogens surrounding a central element. And we don't really know anything about these. You may not have even recognized the last two as acids at all. Again, done on purpose. So let's think about it. Which is your most electronegative here? O, S, or Se? So let's look at where they are in the periodic table. So we go over here to the periodic table. Notice they're all on top of each other. That's done on purpose. So they're all right on top of each other. So as you go up the periodic table, what happens to your electronegativity? It increases. So which one here is your most electronegative central element? Oxygen. So which one's going to be your strongest acid? Water. Now, which one then is going to be your weakest acid? I see. So I kind of did this on purpose. Like these really aren't acids at all, all right? H2S and H2SE. And we can see why, because they're less likely to lose a hydrogen than water. And we know that water is not a particularly strong acid, right? It's amphoteric, it actually acts as both. And so it's an interesting way of seeing, hey look, those two aren't acids. They're even weaker than water. Okay, now let's do two more normal ones. Similar idea, now some things that actually start looking like acids to you. H2SO4 and H2SeO4. You haven't seen H2SeO4, it doesn't matter. Which one is more electronegative, S or Se? S. So which one is your stronger acid? The one with the more electronegative central group, so H2SO4. Which is probably why we recognize H2SO4 as an acid that we use all the time and do things with. We don't really recognize the H2SeO4. There's also a mildly way of kind of cheating a little bit on this one. What's that? What do you know about H2SO4? Yeah, it's one of the ones that we're considering strong, so that helps out. We may have already done this one. I jumped ahead of myself a little bit, but that's okay. We'll look at it again. So it's done in a slightly different form, right? It's done in this condensed formula instead of me drawing it out. But what do we recognize right here? COOH. And then this is a carbon that's off that carbon. Here we have one chlorine, and here we have two chlorines. Which one's your stronger acid? The one with one chlorine or the one with two chlorines? One, two. And if I were to add a third, what would happen? It'd probably be stronger. We may get into some weird other things that happen there, but probably. Okay. So quick review on this. And then this will be the, we'll do some review afterwards. All right. Your strength of your hydrohalic acids are going to decrease as we go up the periodic table. So HF is our weakest, HI is our strongest, and that's because of bond enthalpy, okay? That one doesn't necessarily fit the stabilizing anion pattern because HF, actually, that fluorine likes having that negative charge, but it's all about bond enthalpy for the hydrohalics. So because of that, HF is your weak one, and then as you go down, they get stronger and stronger and stronger. And as soon as you hit HCl, they're strong enough that we consider all of these three strong. Our oxoacids, we have two different issues. They're stronger if you have a more electronegative group in the center. And they're stronger if you have more attached oxygens. In other words, higher oxidation number. We'll get to that later. And your carboxylic acids, those are going to increase depending on what your R group is, or decrease actually. There are some things you could do to decrease the strength, but we're not going into that in this class. So we're just going to say, okay, well, you can increase the strength of a carboxylic acid by adding in an electronegative group, because it's going to pull the electron density toward it. All right? Because of where this particular exam is cutting, we haven't talked about KAs yet. So you won't really get any KAs on this exam. In later exams, like the final, you'll be given a lot of KAs. And later on, we'll find out how you can do a lot of what we did here using the KAs. But I promise you there will still be some where I ask you to rank them, and then I don't give you the KAs for the ones that I give you, so that you still have to understand this. Also, these do generally tend to be the types of questions that I ask hows and whys on. So I did get a good question after the last talk where I said, okay, here's the structure of the exam. So let's review that actually. We're done with new stuff, so I don't know. We'll do some review, but I want to talk about the exam first. The structures of my exam generally is we have a long answer section, we have a short answer section. The short answer section is all or nothing. Significant figures, except for the whole when using logarithms issue, matter. Units matter. Everything matters. We don't have you show work for it. I don't care what you do to get the right answer, except no looking at your neighbor. But other than that, the long answer section, on the other hand, you show work. You do get partial credit. And a lot of times, they're essays. And I think maybe I need to put essays in scare quotes here, meaning don't write full sentences unless you really feel like you need to. Phrases are fine. You don't need to have like super proper grammar. It's not long. It's like 2 to 3 sentences on explaining something. So these are the sorts of things that I talk about up here, right? When I say something like, the oxoacids, if you have a more electronegative central group, it stabilizes the anion, and I give all of those explanations, and then I give you the short answer at the end. Those explanations are important, and that's the sort of thing I test on the essay part, okay? It's hows, whys. You get a lot of practice ones in the mastering. All those questions that I don't grade that are like essay boxes, those are the sorts of things that I ask. So good ways to study for those, because those are usually the ones that people make it a little lost on exactly how to study. Walk through my slides and just act like you're teaching somebody it. Better yet, find somebody in this class and teach it to them, and then teach backwards. So you teach them, they teach you, and if you look at them and say, I don't understand what you just said, that didn't make any sense, it helps out a little bit. So best way of learning anything is teaching it. And that's probably the best way to study for this, for the essay type questions. Okay. This PowerPoint is not posted yet, but it will be. I will post it in completeness. No missing information, nothing. Really, there's just sort of 2 main topics I want to cover. One of which is this one, for a couple of reasons. One, there was some silly calculation errors, so it's worthwhile fixing it. 2, I think there's still some confusion on it. It's the one that by far and away the survey responses came mostly about. And I actually haven't been asked it a lot in office hours, and I'm worried that's because it got skipped a little bit, because it's actually in a different section of the book. You may have noticed that our curriculum doesn't match the book curriculum. You've already done the next chapter, right? You've already done the enthalpy chapter in 1B. And so because of that, we do miss some things here and there. And so I thought this would be a good first thing to do. Okay. So this is using that ratio, kind of a ratio, of what happens as you change temperature, what happens to K. We derived the equation. It was effectively just a 2-point formula of that. So think back, 8th grade algebra or 9th grade algebra, and 2-point formulas. That's how we derived it. So the derivation part here isn't super important. It's how you use it that's important. 2 different ways to use it. I didn't actually do an example of the one, and I'm still not going to because it's kind of boring. The one way that you can do it is legitimately just plug and chug. So if I were to give you a table of values instead of a graph, and just give you a table of values, give you 2 different temperatures and a K, you can see how you'd fill it in, right? If I give you 2 different temperatures and 1 K, you can see how you'd solve for the other one. If I give you 2 Ks and 1 temperature, and you can solve for the other one. And that's really nice before like the advent of computers, where we graph things all the time, and when you're doing these in the lab and you're doing this in real life, if you're going into chemistry, you are going to graph it. So I tend to like the graphs a little bit better. Now the slopes are different. There's 2 different slopes here, right? One's positive, one's negative, and that's an interesting thing to note too. And we can just match it. The kind of fast answer to all of this here is, if it's a negative slope, is it an endothermic or an exothermic reaction? Endothermic. If it's positive slope, is it an endothermic or an exothermic reaction? Exothermic. And that's I suppose nice, but not super helpful in understanding what's going on. So let's think about the formula and what's actually happening here. So we have our slope, which is coming from here, and it's a negative delta H over R. Negative delta H. Well, think back to what we know about delta H. Delta H tells us whether something is positive, or excuse me, the sign of delta H tells us whether something is endothermic or exothermic, right? So if something is endothermic, what's the sign on delta H? Louder? Positive. If it's negative, so it's the other one. All right, so let's talk through this and relate this to Le Chatelier's. Okay, this comes from Le Chatelier, not exactly from Le Chatelier's, but it comes from the same idea. And so hopefully this might make it make a little bit more sense other than just, hey, let's look at the equations. So first question. As T increases, so T is getting hotter, which way does the reaction shift? And what happens to K for an endothermic reaction? Okay, so it's endothermic. Are we treating, for Le Chatelier's principle, are we treating heat as a product or a reactant then? A reactant. And if we're raising the temperature, which way is that going to shift it then? To the products or to the reactants? To the products. Okay. For all our other things dealing with Le Chatelier's principle, that changed the amounts of the reactants and the products. And that's true here too. It didn't actually change K though. Temperature is different. In temperature's case, we're changing K. K will change. So if it's shifting to the products, what is K again in the most simplest of terms? Is it products over reactants, reactants over products? What is it? It's products over reactants, right? Okay. So K is products over reactants. So we shift toward the products. What happens? Does K get bigger or lower? It's bigger. Okay. Now let's think about what happens in the other option. If something is an exothermic reaction, okay, something is an exothermic reaction, is heat a product or a reactant? It's a product. Okay, and we're increasing temperature, so it's like we're increasing a product, kinda-ish. Which way is it gonna shift? Reactants or products? Reactants. Okay, so now instead of shifting toward the products, we're shifting it toward the reactants. Are we making the numerator bigger or the denominator bigger in K? The denominator, the bottom, right? So what overall is happening to K then? It's decreasing. Okay, well that right there shows us why these slopes are opposite sign. Because in one case, if we add heat, if we change the temperature, K increases. In the other case, if we add heat, it decreases. So the slopes are going to have to be different. Again, I'll post this, so if you don't want to write every single word, you don't need to. So because the sign of the enthalpy is different, your slopes are going to be different. All right? And this, Le Chatelier's principle there, explains that for us. Now, with that being said, you don't actually have to memorize the slopes, which one's endothermic and which one's exothermic, because all you need to know is that the slope is the negative delta H over R, and you can get it. Because here for an endothermic reaction, what is your delta H? Is it positive or negative? For an endothermic reaction, it's taking in heat. It's positive. So the slope is always the negative delta H. So if delta H is positive, what's your slope going to be? Negative. For an exothermic reaction, it's the opposite. What's the delta H for an exothermic reaction? It's negative, right? It's losing heat to the environment. So it's negative. And so the slope is going to be the opposite of that. So negative of a negative is a positive. It goes up. So that's how you can remember which one's which without having to memorize it. Now, so for an example, let's do this one. So we did an example like this in class. It was just the opposite sign. So is the reaction endothermic or exothermic? Explain. Now, here's how you don't explain. You don't explain by saying it has a positive slope. Okay? You gotta do a little more than that. So first off, our slope is always gonna be what in variable terms? Negative delta H. Our slope here is what sign? Positive. So what does that mean our delta H is? And so it's exothermic. And then what is delta H? We just need to do a quick calculation for that one, right? We know that our slope is negative delta H over R, which means that our delta H is negative slope times R. And which R do we use? Which R do we use? 8.31, right? Okay, and we get our answer. And it's really big. That's not particularly surprising, right? Because what do we normally actually use for units on delta H? Yeah, when you look them up in tables, they're generally in kilojoules. So the fact that it's huge isn't a big deal. That's pretty standard. Okay. Hopefully that clarifies that up a little bit. The second, yeah. So as far as like kilojoules or joules or milligrams or grams or any of the sort of conversions between particular units like that, if I want it in a particular unit, I'll tell you. Otherwise, generally the easiest thing is to just leave it in whatever it comes out in this case joules per mole. But if you convert it, it's not wrong. Those are the sorts of things that might get it a misgrade, and you might have to do a regrade, but that's not a big deal. I fix those up. Okay, so the last 9 minutes, and I'll post what we don't get through. This, I think, messed with a lot of people, a lot more than I necessarily anticipated. So how to deal with limiting reagents when you're dealing with equilibrium. So I think we probably did this in every single office hours since day one. So I thought I'd talk about it a little bit. There's two different situations that can arise when this matters. First off, let's talk about when it doesn't matter and when we don't have to worry about it. If you have a reaction that has all either gases or aqueous species, depending on what you're dealing with, this doesn't matter. You don't have to worry about it at all, okay? That being said, if you have a heterogeneous mixture, which means you have solids or you have liquids, now you have to at least think about whether you need to worry about this. Sometimes you will, sometimes you won't, okay? So if it's all gases or aqueous species, don't worry about it. The equilibrium mixture will do its thing, and it doesn't really matter. What does matter, I should specify, as long as you have some of everything, you'll be fine. Where it does matter is something like this, where we have solids and gases, or solids and aqueous. And the reason for that is that your solids and your liquids are not a part of your K, right? And we remember that. We remember that, okay, whenever we write a K equation, whenever we do those calculations, we don't include solids and liquids. Because of that, now we have to deal with the fact that we could have a limiting reagent that does affect our final answer, but never goes into K, because these aren't included in K. Everything else, it gets put into K and it shows up there. All the things that happen to it will affect the K. This is different. So the homework problem like this that you had was the one that had graphite in it. I changed things around a little bit, but. So again, this will be up. It's basically just the same thing I just said. The amount of this and this doesn't matter as long as you have enough left over. So as long as you have enough left over that it's not a limiting reagent, it doesn't make a difference. As soon as one of the solids become a limiting reagent, now you have an issue that you have to deal with, a slightly different. It actually makes your calculations a little easier in my opinion, but you have to recognize that it's happening. Okay, so we're gonna do two examples. In these two examples, I am actually going to, come back. Hang on, it just disappeared on me. Okay, there we go, it's back. I'm gonna tell you which one's limiting. For the record, I would absolutely not do that on an exam. I just wanna do it here for the sake of, this is when you have to worry about it, okay? So let's first look at what happens if your gas is your limiting reagent, all right? If your gas is your limiting reagent, pretty much nothing, it doesn't change anything. You treat it as a normal equilibrium problem. Because what this means is that you're gonna have enough of the solid to get up to the point that your Q and your K are equal. Or in other words, you're going to have enough of your solid to react to make sure that you have enough gas to actually reach equilibrium, okay? If you don't have enough, then we'll talk about that next. So let's look at this one. I have 56 grams of CaO is mixed with 22 grams of CO2 in a 0.1 liter container. Find the concentration of CO2 and the amount of moles of CaCO3 formed. So we're going to do two things. The first one, really, really nice. The reason is because what is our Kc equation for this? CO2. That's it. Which means that Kc, well, close, 1 over CO2. Which means that Kc, which is always equal to 0.3, is just equal to reactants over products, which is just equal to 1 over CO2. Well, that means that the pressure of CO2 is always constant, as long as there's enough. And there's a key phrase there, as long as there's enough, right? Okay, so we just take 1 over the concentration of CO2, or Kc. So 3.33 molar, as long as there's enough. Now, let's look at what happens though when we go to find the moles. Notice I do say moles of CaO3 formed, that's just to make the problem a little shorter. Ignore those X's for a second, the ordering is a little mixed up. Whenever we go to solve these, we probably want to look and see which one's limiting first. If you're really good at catching mistakes, you may just want to go through them and treat them all as equilibrium problems and then catch the mistake afterwards. Generally, it's not the best idea though. So let's convert each of these to moles. Those are some convenient numbers. So I just divide by the molar mass. Now, if I want to fill this into an ice chart, I need to make sure I divide by liters, right? So that gives us 5 moles per liter. Because we're doing an ice chart, I'm not really going to bother with this. The only reason I calculated this is to decide which one's my limiting reagent. So these react on a 1-to-1 ratio, right? One of these reacts with one of these. So since this is a 1-to-1 ratio, which one has to be our limiting reagent? CO2. We have enough solid. As long as we have enough solid, we don't really need to worry about it. We just need to now make sure that we have enough CO2 to have actually reached equilibrium. So that our answer on the previous slide may make sure it's correct. So now, we have our minus X. We need to see, was that enough or not? Are we actually at equilibrium or not? Because otherwise our answer on the last slide wasn't right either. And it is, because right now, our Q is going to be less than K. If we take 1 over 5, our Q is less than K. And so it needs to shift toward products. It needs to get bigger. So our answer on our last slide was okay. That wasn't true. That means we didn't have enough to ever reach equilibrium, right? If we don't have enough to reach equilibrium, well, can't do anything. So we have enough to reach equilibrium, so that's fine. Now, we go ahead and do this just like normal. I knew these were minus X because my Q is less than K. So that means this has to be plus X. Well, it's nice because our reaction is just 1 over 5 minus X. So that makes for some much nicer algebra than we've had to deal with in the past. One thing that comes up with the algebra on these a little bit that you should be careful of, when you multiply this up, don't forget to distribute the 0.3. It's one of the silly errors that happens a fair amount. And we find X. Why did I solve for X? Like, why did I care about my amount of CO2? Did I ask about that? Yeah. But we already knew this anyways. It's always going to be the same number. So we didn't really care about this. Why did I solve for X? Yeah, I want to know this, right? I want to know that plus X. The problem is does it make sense to say that's 1.67 moles per liter? Is this 1.67 moles per liter? It's a solid now, right? So I don't want to use moles per liter. What do I actually want to do with that X? I want to look at moles. So I got this because of the CO2. Even though I really care about this, I got it because of the CO2. I already know this number. So I got it because of the CO2. Now I say, well, my change in moles are going to be the same. So I multiply it by my 0.1 liters, to get my 0.167 moles. That's my change here in moles. And then I'm all done. There's another way you can do this too, but we're out of time. So I'll post up the rest of this problem. So the next part of this problem is so that you can do it when the other one is limiting. And I'll post it up and I'll annotate it a little bit more too, since we didn't quite make it there.